So we're going to focus on continuous functions and continuity, and when functions are not continuous. And this is the limit definition of continuity. A function is continuous if limits equal function values. Typical functions that we deal with are continuous everywhere. You know, this is a function that's continuous everywhere. Every single spot of this function, I have a function value and I'm approaching that function value from the left and from the right. Okay? And when functions have discontinuities, they're usually just at one spot. They're usually not discontinuous for like an interval. You know, you have a certain, asymptote or something else, and it's only at that point right here at this x-coordinate that we have a discontinuity. Here the limit doesn't exist, so the limit is not equal to the function value. And what are the situations where this can occur? At a hole. Now it's important, this function, you know, to the left of the hole, to the right of the hole, is continuous. It's just only at this point C where the function is not continuous. So, not continuous at x equals C. Using the limit definition, you could say it's not continuous because f of C is undefined, even though the limit is defined. You could have a jump for jumps, whether or not you have a closed circle or open circle. Continuous everywhere except for at this location of the jump, at C. Again, it's not continuous at x equals C. Why is this? Well, in this situation, the limit as x approaches C doesn't exist. So the whole limit equaling function value is impossible. And then we have vertical asymptotes. Again, this function is continuous everywhere except for at this one location. Okay, so these discontinuities are just at specific locations. And again, it's not continuous only at C. And in this case, the function value doesn't exist and the limit doesn't exist. Now, we will describe a hole as a removable discontinuity. We will describe jumps and vertical asymptotes as non-removable. One way is to reason why is this removable and these non-removable. If I can just take one point, can I move that one point and make this function continuous? I can here, I can't here, I can't here. Okay. Also, for a vertical asymptote, we call this a non-removable infinite discontinuity. Okay. Now, when is a function not continuous? Like if I give you an expression f of x and I have some version of x's, you know. Typically, when the function values don't exist, when the function values are undefined, and we are not allowed to have zeros in denominators. So typically, it's when your denominator is equal to 0. If you're just talking about one function, f of x is equal to x. How do I know if it's going to be a removable or non-removable discontinuity? Well, if you have a denominator that's equal to 0 and you have a 0 above it, that's your indication that we have a hole. It's not always going to happen. I'll show you one example where it doesn't. But when we have a hole, we call this a removable discontinuity. If we end up simplifying or plugging in a value and we end up with a number over 0, this is your indication that we have a vertical asymptote or an infinite non-removable discontinuity. Now, what about jumps? We'll get to that. These are functions. F of x is equal to some expression of x's. When is the function not continuous? State the type of discontinuity. It's very, very simple. All we need to do is start out by setting the denominator equal to 0 and solving. Here, x equals 1. Easy enough to solve. Now, the type of discontinuity. Well, that's easy to find too. If you just analyze the function value at 1 and realize that I get 0 over 0, that is telling me that this x equals 1 is removable. It's the location of a hole. For this guy, x squared plus x is the denominator. I would set this equal to 0. Figure out which values of x would the denominator equal 0. Those will be the locations of discontinuities. I get x times x plus 1, which I need to do to solve, factor, and I get both 0 and -1 are discontinuities. Now, which one is which? What kind are they? Plug in 0, I get 0 over 0. That's telling me that at 0, we have a removable and if I plugged in -1, I'd end up with -1 over 0. That is telling me that this is non-removable and it's infinite. Okay, next one. It's really the same deal. You know, you just set the denominator equals 0 to factor solve. You guys could do that while I'm doing it, and we'll check our answers together. All right, we got two. One's removable, one's not. Well, now I get to this one. It's the absolute value of x minus 3 over x minus 3. And we set this equal to 0, and the denominator, that is, and I get x equals 3. And if I plugged in 3, I get 0 over 0. So indications are we have a hole. But this, my friends, is the only type of function that we have to know about as an expression of x's where 0 over 0 does not mean hole. Okay? We should be aware that this is the type of function where if x's are bigger than 3, we just have x minus 3 over x minus 3, which just gives us values of 1. And when x is less than 3, you take the opposite of whatever you have in the numerator, x minus 3. If x is less than 3, like 2 minus 3 is -1, the absolute value turns that -1 into a positive 1. So I actually take the opposite of this x minus 3 when x is less than 3, divide that by x minus 3, they cancel, and you get negative 1 to the left of 3. And here is a situation where x equals 3. That's a jump. Non-removable jump. Even though it's 0 over 0. Okay, it's something over itself, but it's something that's positive divided by something that will be the same value that could be positive or negative, which is why we're going from negative 1 to positive 1. Okay? So, go back. Jumps, when you have these, absolute value of something divided by itself. Those are ones you have to be familiar with. Yep, same exact thing. Okay, there's other versions of it as well, where you have like x over 2x, and then you'd be at positive a half or negative a half, stuff like that. Okay? But all other functions, you get 0 over 0, boom, assume it's a whole. But jumps occur a lot more frequently with different types of functions, not with necessarily f of x equals some expression with x's. What different type of function produces jumps when we look at them? Piecewise functions. Okay, so fantastic. Either something like this or piecewise functions. Okay? And when we're dealing with piecewise functions, it's important to know, it's important to see that, hey, look at your individual pieces. X squared, this is going to be continuous everywhere that I use it. There's no denominator. There's nothing crazy going on. 2 minus x, that's going to be continuous everywhere. So I actually don't have to sketch all of it. I don't have to see this, that it looks like this in this shape. I don't have to see that this looks like this shape. All I need to make sure is that this piece connects with that piece. And if they connect, it's continuous. If they do not connect, we have a jump discontinuity. Okay, so this is all we have to do. We don't have to really sketch or anything. We just need to check to see if the pieces meet up. So don't worry about sketching. Sometimes it helps us, but all I need to do is say, okay, this piece, I'll call it f little 1. Does that meet up with this piece where I leave this one and pick up this one? That's at 1. Does f little 1 at 1 meet up with f little 2 at 1? And in this case, it does. Since they meet up, we can say, oh, this guy's continuous everywhere. Okay, you guys do the second one while I'll do the second one. We'll check our answers. So figuring out that at 1 they don't meet up, the x squared plus 3 and the 10 minus x, I know that x equals 1 is a jump discontinuity. Or it's a non-removable jump discontinuity. All right, let's look at this guy. Sine of pi x for absolute value of x, which is less than a half, and 1/2 plus x for the absolute value of x is greater than or equal to 1/2. This seems interesting. Well, let's start by thinking about possible values that we can use for x if the absolute value of x has to be less than 1/2. Shout out a value for x. 0. Okay, good. Give me another one. 1/4 works. 1/4, its absolute value is 1/4, less than a half. Okay? Would be another one. Negative 1/4. Okay. What about 1/8? Negative 1/8. Okay. So it appears that if I look on a number line, even though I just have this positive a half, these negative values that will go up to, but not include negative 1/2, are also included. So it's like I have the sine of pi x inside those two numbers, and I'll be using it for that. I don't know why I did my fractions two different ways. It looks messy. Now let's think about values for absolute values of x's that are greater than or equal to 1/2. 4, 5, 6, 7, 8, et cetera, et cetera, et cetera. But also -4, -5, -6, -8, all of those as well. So actually, this 1/2 plus x is going to be used for these values to the left of -1/2 and for these values to the right of positive 1/2. So even though this piecewise function appears to just be focused on one location, because of the absolute value and because we take our negative values and make them positive, we actually are focusing on two locations. And we have to see if the first piece meets up with the second piece at -1/2 and at positive 1/2. So let's see. Does f little 1 at -1/2 equal f little 2 at -1/2? I have sine of negative pi over 2. Does that equal 1/2 plus 1/2? Sorry, 1/2 plus -1/2. Sine of negative pi over 2 is -1. 1/2 plus -1/2 is 0. So no. Let's look at positive 1/2. Does f of 1 at positive 1/2 equal f little 2 at positive 1/2? Well, does the sine of pi over 2 equal 1/2 plus 1/2? In this case, yes, it does. So actually, sometimes it helps to see the graph of this one. The 1/2 plus x will stop at 0 when I get to -1/2. The sine starts at 1, goes through 0, and ends up at -1. Sorry, it goes to -1 to 1. Starts at -1, goes through 0, ends up at 1. And then it picks up the line 1/2 plus x from there. So we have a jump at -1/2. Non-removable. It's a discontinuity. This is not great. Something like that. All right, if you have space, or even if you don't, line space. Add this to your notes. What about this situation? So this is kind of a piecewise function, but actually kind of not, because we are using the top piece for every single x value except for at -3 and 2. We're using these individual points at -3 and at 2. At -3, I have -1/5, and at 2, I have 1/4. Now, for this function to be continuous, whatever the top piece looks like, I don't know what it looks like, but if it passes through those points like that, well, then we'll be continuous. So the first thing we should try to do is plug in 2 and -3 into that top function and see, does f of little 1 at 2, does that equal 1/4? Does f of little 1 at -3, does that equal -1/5? Let's try. So I'm going to do f little 1 of 2. And I get 5 over 4 plus 2 minus 6, that's 0. So no. But what is that telling me? The vertical asymptote, not a hole. When you have a number over 0, vertical asymptote. So that means, and we could do a little bit more analysis if we wanted to, but if I looked at just graphing this piece, I would get up to, but I would never go through any point at 2. So automatically I know we have a discontinuity at 2. That hole, that dot right here at 2 1/4, it's not going to help anything. Okay? So x equals 2 is definitely a non-removable discontinuity. But let's try f of -3. Well, f little 1 of -3. And I plug that in, I get 0 over 0. So this function of itself has a hole at -3. But I don't know where the hole is located, and if all is right in the world, maybe the hole is located exactly at this point where we have -3, -1/5. And maybe that point fills in the hole and my function is continuous there. So what we need to do is we need to make sure that this function approaches -1/5. We have to see if it does or not. And I could see, hey, what is the location of this hole? And we can find the location of that hole by finding the limit and using our algebraic processes to find this limit. I plug -3 into the simplified 1 over x minus 2, I get -1/5. So that means, yes, if I just graphed this, I would have seen a hole. But that hole is actually located right here at -3, -1/5. So this point fills in this hole, which means this function is continuous at -3. It's only not continuous at 2. Okay, so I put that on your notes for a reason. take what you will of that. There are other types of questions. There are some types of questions where I say, hey, let's make sure these pieces of these piecewise functions meet up. Let's make sure x squared minus c meets up with 4x plus 2c at x equals 5. But I need to make sure I have the correct c so that happens. Okay? So what we are doing is just find the values for c, not x, or a, or b, these other variables, to make sure that these pieces meet up. So, just like before, we know they're going to be continuous because they don't have any denominators. I just need to make sure they meet up. Make sure f little 1 at 5 meets up with f little 2 at 5. It's important that we see that, we're plugging in the x values in for x, not in for c. Some people will make that mistake, but it should be 25 minus c equals 4 times 5, which is 20, plus 2c. Okay? And then we solve. Subtract 20, add c. I get 5 is equal to 3c. Divide by 3, c is equal to 5/3. Okay, you guys can do the second one while I'll do the second one and we can check our answers. You guys get 2/3? Yeah? Good. Okay, well, sometimes you won't just have an A. Sometimes you'll have an A and a B. And let's do the one on the right, and we'll go back to the one on the left. Well, to find both an A and a B, I'm going to need two equations. I'm going to need a system. So this is reviewing solving systems. Well, for this to meet up with this, you're going to have to meet up at -1 and then at 3. So let's make sure we set up the correct equations. Top piece meets up with the middle piece at -1. I get 2 is equal to -a plus b. Middle piece needs to meet up with the bottom piece at 3. I get 3a plus b is equal to 6. I have two equations and two unknowns. To be able to find these unknowns, we have to use the equations to help each other. Two ways to solve this that we've learned from the past. One way is substitution. With substitution, I would take one of my equations and solve for a variable. Let's say b is equal to 2 plus a, or 2 plus a is equal to b. And then I would take that and substitute it into the other equation, giving me 3a plus 2 plus a equals 6. That eliminates one variable, allows me to solve for the other. That gives me 4a equals 4, or a is equal to 1. Once I have that, I may go back and substitute it into one of the previous ones. Doesn't matter which one. If a is 1, b is 3. Okay? The other method is elimination. Depends on the situation which one is easier to use. With elimination, we stack the two equations on top of each other. so that the variables are lined up. 3a plus b is equal to 6, and negative a plus b is equal to 2. Now, our goal is to add these two equations together so that one of the variables is eliminated. Now, if I add these two equations right now, I'd get 2a plus 2b equals 8. That doesn't help me. But if we multiply one or both of the equations by a value, could be -1, could be +2, could be anything. But I'm going to multiply this top one by -1 because that'll create opposite b's. And then when I add the two equations together, the b's will eliminate. I have -4a is equal to, this will be -4. That gives me a is equal to 1. Take that, plug it into either equation, and you'll get b. Okay, so just a little bit of review. If we have time, we'll go back to the previous one and do it. The answer's not super nice, but it's fine. Add this guy to your notes. So similar to the last one, you guys should be able to do this. What does b have to be so that this function, g of x as a whole, is continuous? Well, if I tried to plug in 3 into the top one and see if it met up with the bottom one, I get 0 over 0 equals 9 plus b. What is that telling me? That this function has a hole at 3. We need this point to fill in the hole, which means finding the function value isn't the way to go about things. Rather, find the limit. See where the location of the hole is, and that will help you. This is a 9. So don't do this, do this. Does that make sense? These are tricky. Like it looks like a piecewise function, but it's not. It's really just like use this everywhere except for one point. Well, they purposely say use this everywhere except for the location of its own discontinuity. I set the denominator equal to 0. I know I have a discontinuity here of 3. But it's like, oh, that ends up being a hole, which means we can fill in the hole with a point. Let's make sure we do that. So it's just kind of more limit questions from the first unit applied differently. This is a tricky question. I wanted us to look at this question. You may see it in the future. What positive values for A is f of x continuous? Why don't you discuss this one with your neighbors? Can you figure out a value for a that's positive so that this function is continuous everywhere? Go ahead and discuss. So obviously it can't be 4 or 9 because that doesn't work. So why doesn't that work, Mr. Collioure? Yes, that's exactly right. So some people's first instincts are, oh, 9, right? Because then these cancel out. Well, yeah, sure, but if we just look at the function before simplifying, when is a function not continuous? When your denominator equals 0. This equals 0 at plus or minus 3. Okay. So at 4, that also doesn't work, plus or minus 2. But like, what about 8? Can you plug in a value? Can you have x squared minus 8? Can this equal 0? Yes, so you can actually solve that. You get plus or minus root 8. So you wouldn't have a hole, though. In this situation, what would you have? If I had x squared minus 8. I'd have vertical asymptotes at plus or minus root 8. I would have holes if it was x squared minus 9 because I'd have that 0 over 0. But at root 8, I'd have a number over 0. Okay. One? No, that's not going to work. Plus or minus 1. Anything? Nothing. It's a trick question. Okay? Because there will always be values for x if it is set up like this, x squared minus a. There will always be values for x to make the denominator 0. If a denominator equals 0, there is a discontinuity. Even if things cancel, if a denominator equals 0, it's a discontinuity. It just might be removable or non-removable. No matter what I pick for a, the square root of a can be plugged in and it will make the denominator 0. So this is a trick question. No values. None is the answer. Negative values, now that would be different. Any negative value would work because you'd have x squared plus 1. Can you plug in any value for x here? That's a real number. And solve that? No, you'd have the square root of negative 1. So if you ended up with any negative number and having x squared plus a value, then you would be continuous everywhere. All right. Moving on, whenever we talk about continuous functions, we are going to be able to use a new theorem. It's one of the 2 theorems that we need to know in this class. There's only 2 that are important that we use for proofs. We don't do much proving in calculus apart from using this theorem and another theorem. And this is called the intermediate value theorem. It's IVT for short, and it deals with continuous functions. And it states, if f is continuous on a closed interval between a and b, and k is any number between f of a and f of b, then there exists at least one number c in ab, such that f of c equals k. And that doesn't make any sense to you. But if we draw a picture, hopefully it'll help. What this theorem states is, let's say you have a function, f of x. And let's say you know 2 points on the function. This point here, this point here. I can move them anywhere. Okay? But that's all I know. I know that I have a function, and I have 2 points, and The most important part is I know that this function is continuous. So this guy, f of x, continuous. It just has to be continuous on your interval. Okay? What this theorem states is pick a y value in between these two y values. Okay? Call that k. The intermediate value theorem states that you're going to cross k somewhere between the 2 points. That's it. Our graph, f of x, will cross k at least once somewhere between the 2 points. Oh, that's so messy. F of x will, that's not that much better, cross k somewhere between 2 points. Okay? No matter how you connect it, if it's continuous, these 2 points must be connected somehow. Look, across k, right there. Here is the value that they're talking about, C, between A and B. That gives you this value K between f of A and f of B. Okay? This can be used a lot of different ways. It's typically used to show that something exists. It's like, oh, there is going to be a solution to this tough equation. Even though I might not be able to find the solution, I can at least know in the general vicinity where it is. Take this question right here. Explain why the function has an x value such that f of x equals 5. Okay, well, we want to look at trying to solve this equation. Okay, f of x equals 5. Okay, this is f of x equaling 5. However, you're going to find that if you try to solve this by hand, you are not going to be able to. It's not possible. You're going to have to use a calculator, some numerical calculation device to find this solution. Okay, not everything is solvable by hand, which you don't think of if you do high school maths. Okay, but we don't care about the actual solution. We just care to know if one exists. Well, they gave me 2 points, 1 and 2. Why don't we just investigate these 2 points? Let's plug in 1 into this function. I get 4 minus 6 plus 3 minus 2. That's negative 2 plus 1, which is negative 1. And let's plug in 2. Well, I got 4 times 8, which is 32, minus 6 times 4, which is 24. 32 minus 24 is 8, plus 3 times 2 is 6. 8 plus 6 is 14, minus 2 is 12. So f of 2 is 12. So what's that telling me? Well, that's telling me that this function has 2 points, 1, negative 1, and 2, 12. Do we have to pass through 5 if this function is continuous? Yes. So where's 5? 5 somewhere here. How do you connect these points? I'm not sure. I mean, it's an x cubed. It's probably going somewhere like that. Okay? Where is this location? I don't know. Where we equal 5. I don't know. But I know that it has to exist. And that's the intermediate value theorem. there must be some x value between 1 and 2 such that f of x, when I plug in that x value, gives us 5, because 5 ends up being 12 and negative 1. We probably should be comfortable writing a statement that explains this right here. And the statement must include a discussion about the continuity of the function. So you'd say, like, since f of x is continuous, you'd probably repeat the points that you found. F of 1 is negative 1. F of 2 is 12. There must exist. Now, it doesn't mean we'll be able to find it. It doesn't mean there's going to be one. There must exist at least a x value between 1 and 2 such that s dot t dot for short, f of x equals 5. By the intermediate value theorem. Okay? That's the intermediate value theorem. It's all about continuous functions and connecting points. If you do some homework problems, they might ask you to show that it exists and then actually find the solution. This first one's easy. Okay? Show me that f of x equals 0 somewhere between 0 and pi. Well, using the intermediate value theorem, you can go straight to finding the solution. But using the intermediate value theorem, you would first need to show that this solution exists. So I start with using the 2 points, my boundaries, f of 0, which is the cosine of 0, which is 1, and f of pi, which is the cosine of pi, which is negative 1. And I know that the cosine function is continuous everywhere. That's important. All right. Through that quick analysis, finding 2 points and knowing that the function is continuous, I know for sure that there is some x value between 0 and pi such that the cosine of x is equal to 0. Because 0 is between 1 and negative 1. What is that value? Pi over 2. Okay? So it exists. We knew it existed. And boom, we found the solution. Okay? That one was easy enough to do. This one, not as obvious that this function equals 6 somewhere between 2.5 and 4. Let's do some work here. Oh, this will be fun. We get 25 fourths plus 5 halves over 5 halves minus 1. That's 10 fourths plus 25 fourths. That's 35 fourths over 5 halves minus 2 halves is 3 halves. That's 35 times 2 over 4 times 3. Cancel 2. 35, 6? That's fantastic. What the heck is that? What is 35 divided by 6?
That would be about 5.8333.
5.8333. Thanks, Siri. Okay. What's f of 4? That's 16 plus 4 over 4 minus 1. That's 20 over 3. We can do that. That's 6 and 2/3. Okay. I got 2 points. 2.5, 5.8. 4, 6.6. which means we're surrounding 6, this number here. Okay, good. But is this function continuous?
In our interval.
Ah, very nice, Mr. Kalia. It is not continuous everywhere. At 1, it has a discontinuity, but it is continuous between 2.5 and 4. So we check off the continuity part. Continuous on this interval. Fantastic. Which means we know that the solution exists. Let us find the solution. Let's solve. Let me just take this and shrink it down a little bit. Let's solve this equation. X squared plus x over x minus 1 equals 6. What should I do? Yeah, let's multiply both sides by x minus 1. And I'll remove it from the left side. On the right side, I'll have to distribute it. Ooh, I got x squared plus x equals 6x minus 6. What do I do now? Factor out an x from the left side? It's a quadratic, so what should I do? Yes, move everything onto one side. I don't think we've solved the quadratic here in this class yet, so this might have been like, oh yeah, that's what we do when we have x squareds and x's. Okay, it's a quadratic. We have to either factor to solve, use the quadratic formula to solve. Thankfully, we won't have to use a quadratic formula ever in this class. We only have to factor. We get 2 solutions, 3 and 2. All right, well, there's 2 solutions. I don't like both of those solutions. I don't like one of them. Which one do I like? 3. Why, Mr. Schaefer? 3 is the solution guaranteed by the intermediate value theorem. It is the value between 2.5 and 4. F of 3 is between 2.5 and 4, and that's equal to 6. This is like an intermediate value theorem problem. Let's say our function's continuous. Give one value for b so that the function must have 2 roots. What's a root? Root is a 0. It's an x-intercept. I got the points. -1, 3, 1, something, 3, 5, 5, 4. Somebody give me a value. -2. Yes, if we're continuous, we must pass through the x-axis twice. If that's the case. So any negative. All right, that's good. What if I must have 1 root? And I must have 1 root, and that root can't be 0. I can't have this point here. This is not allowed. Can't be 0. Somebody give me a value for b. Yep. There's an infinite amount of them. So I can't have this point here. Can't have that point here. Nope. Nope, no jumps. Function's continuous. Let's just assume this is continuous. Can't be a negative because you're going to cross through twice. Can't be 0. I told you it can't be 0. 1/2? Sure, that's fine. Is there another one? Yeah. Yeah, it could be any positive number. Now it might not must. I guess that problem was must was the bad. That could. So that's my fault. That's my fault. No, sorry. That was tricky. Yeah. No. Could, not must. Okay. That was just me throwing on some extra stuff there.